Welcome to Advanced Data Analysis with me, Erik, Erhardt, Professor of Statistics at the University of New Mexico. In this video, I will help get you started with the coding and the plotting for Chapter 5 of Introduction to Modern Statistics, Exploring Numerical Data. We're going to be using this supplement, which is a Quarto QMD file. And this video is basically a continuation of the previous video. I will assume that you have watched that one and not cover any of the same material and just focus on what is new for numerical data versus the categorical. So let's start by downloading the supplement into your ADA1 folder, and we'll go over to RStudio and open that file, and as always, set the working directory to the source file location and render it. Make sure that everything's working. All right. Okay, it completed. It generated a, let's go find it. There it is. An HTML file. There it is at the bottom. So, and if I just page through quickly, it's got a bunch of plots in there. All right, including some maps. So let's go over to Chapter 5. We will, there we go, zoom in a little bit more. I don't know which way is better. Anyway, so we're going to make some of these plots. I'm just going to walk through the code for doing so. So in the editor window, there is a set of packages that we need to run. In addition to the tidyverse open, these are basically packages I discussed last time. There are many fewer because categorical data require some special consideration, so there are more packages for the categorical data. All right, our first plot is just a simple scatter plot. What do we need to encode? We need to encode total income as the X variable, loan amount as your Y variable, and that's it. There's some additional formatting about the scales, so the data are in thousands of dollars on both axes. All right. So we've got this data set called loan 50. There it is. It's 50 rows of probably the 50 states. Looks like a person's annual income, debt to income ratio, whether or not they rent or have a mortgage, and then there's some additional variables down here. Total income, I think, was one of the ones we were going to do, right? Total income versus a loan amount. Loan amount is also down here. Okay. So we're going to take those two variables and encode them to total income to the X variable, loan amount to the Y variable. Let's start there. That creates just a set of axes where the boundaries are, just inside of the range of the data for both the X and the Y axis. Geom point is what's going to give us the points. Okay, alpha equals 0.6 is the opacity. It's the inverse of transparency, or the complement of transparency. If we remove that, the opacity of every point is 1. You'll see them darken up. Okay, now they are black. The reason for having some transparency in the points is when they land on top of each other, it can be hard to tell when they do. So if we make this a quarter, you can see actually that, there's one point here that's darker than the others. Here's a case where two of them are the same. Here there's two that are slightly overlapping, but it's really when they overlay a little bit more where it's sort of helpful. So I might change that to 1/2 instead of 60%. Then we can see that this one's twice as dark as the others. But it does take a keen eye to pick that out. All right, so now we've got some labels, total income as the X label and loan amount as the Y label. Finally, the scaling x and y on a continuous axis. This is setting labels using dollar format. This comes from the scales package to do these special scales. Dollar format. Notice that the scale is 0.001. So that is converting them to thousands. Effectively by multiplying the number by this scale, right? So if you got 1,000, it would be 1000. But if you multiply 1,000 by this, the 1,000 becomes a 1. Okay. Suffix equals k. Well, that's the k stands for 1,000, right? So if we go to the original, we've got 1 times 10 to the 5, 2 times 10 to the 5, and we've got 10,000, 20,000, 30,000. The new one has multiplied the values and put the k suffix. Great, now humans can read it. All right, that is the first plot. The second plot is very similar. We've got some transparency so that the points, you can see the density of the points. There's these other features too that you can see the outsides of the circles. We'll take a look at that. And we have percentages on the x-axis, and we have a smoothing trend line. So there's a lot happening here, but the basic features are the axes, what object is being plotted, that's the point, and then there's an additional annotation of a line. So once you can deconstruct a plot into its components, you can figure out how to put it together. So this data is county. All right, we've got a poverty variable. It looks like they're doing a transformation right in here by dividing it by 100. That's to create a percentage. Okay, so poverty here is poverty here is already a percentage. They're dividing it by 1,000 to make it a proportion, a number that I prefer to a percentage, honestly. Y is a medium household income. So let's start there and see what happens. We've got just our axes. Then we're going to plot points. In fact, let's just plot points. So I'm going to do this part and close the parenthesis for the geom point. That's the basic plot. All of this stuff is extra. In fact, in your video or in your version, you probably will not have this black here anymore, but we'll just do black. That's sort of anyway, I won't explain it. So we're doing several things here, right? So we've got alpha is 0.3. That's going to lighten the points so that 3 1/3 points is what you'd need to be completely opaque. The color is going to be black. The shape, 21 is an open circle. There are, you can look up our plot characters, characters by number, I don't know. Okay, good. Oh, good. Plotting symbols. Let's take a look at this. And here you go. 21 is, oh, it looks like a big solid circle. Okay. Anyway, so there's, and oh, here's a description of each of the plotting characters. Okay. So that's the shape, and then the size makes it bigger. So if we do just that part, now we've got those solid circles. You know, shape 21, that seems redundant to me because they are already circles. So if I took it away, that is what it is already. Okay. Fill equals black. That is the default. So we don't need that either. Okay, so alpha is the transparency, the size is 3. If we were to make this 6, the size, you'd get really big points. Okay. Then we've got geom smooth. Let's just call this red instead of this thing. Sorry about that. I'll fix that before you see it. Line type, so the smoother is, let's put that down there and close the parentheses. The default smoother puts, I think, a blue line there we go, with standard error bars. That's the gray margin that goes around the blue line. And it usually tells you, yep, the method it's using is GAM, that's a general additive model. That happens because we have a large sample size. If you have small sample sizes, its smoother will be a low S, locally weighted smoother. I forget exactly what it stands for. Anyway, so that's gives you basically the center of the data, roughly. Okay, it gives that trend. We're just changing the line type here to dashed and the red color, and if you do standard error false, you'll remove those gray bars. So let's do those parts. And we just have a red dashed line now with no bars. So now we have a sense of a trend. The rest is pretty easy, right? We've got labels, and then we've got, on the x-axis, we're converting these to percent format, and then we've already done thousands of dollars on the y-axis. So let's just take a look at the x-axis change to percentages. Because it was 0.1, 0.2, 0.3 as proportions, the percent format automatically converted it to percent. Now, if we needed this accuracy to be, say, to the 10th or even the 100th, we could add that to the accuracy, but never add degrees of accuracy that are unnecessary, right? These values themselves are not super precise, probably, because they're measured with some error, and there's also sampling variability that you should probably consider. And so an accuracy of 1, I think, is absolutely sufficient in this case. So 10%, 20%, 30%, no more than 1% resolution. So I like that. All right, let's take a look at the next plot now. Dot plots. So this little triangle is like a little bonus, okay? The basic dot plot is like a histogram, except we're using individual points to represent the values. And it looks here that we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You sort of have room for 10 points along this percent axis as you go from left to right. All right, so the first thing they do is calculate the mean of that variable on the x-axis. So that is 11.56 as the average interest rate. To make this, what do we need for this dot plot? We need an x-axis for interest rate, and we need our geometric object to be dots. That's it. So let's start with those parts. We start with the data set, interest rate on the x-axis, and then geom dot plot. That is the basic plot. You're done. The rest is, just making it fancy. There is here, we're changing the x values, and we're going to change the label to be percentage. So we can add that. So now we've got, instead of, it started off as 10 and 20, and we changed that to 10%, 20%. The rest is taking away, blanking out for the y-axis, the title, the text, and the tick marks. So if we do that part, watch the y-axis over here. That goes away. And then, this is pretty cute. We create a little polygon, right? And when you create a polygon, you need to specify x coordinates and y coordinates. So we're making this little triangle. So we're starting off with, let's see, so these are percentages. So we're going to start off with an x value of the mean value minus 1, and then we're going to go over to the mean value plus 1, and then we're going to go up to the mean. And the y variable is going to stay low and then go up to 0. So you're basically drawing the triangle by going across the bottom and then up to the top point. And it automatically connects the first point with the last point to make the full triangle. And then we're going to fill that with a red color. So there is a little triangle. That's pretty cool. And obviously, like the mean statistically is the balancing point. If every observation had the same weight, it's the balancing point. So if you had a fulcrum and you had like a teeter-totter or a scale, the mean is where those points, the data set would balance. So that's the analogy that's being illustrated there. All right, so let's see what's next. Histograms and shape. So histograms are frequencies that are binned, and then the height are the frequencies within each X range of the data. So we've got a standard histogram, and then we have a density curve. I'm going to show you a few things with the density curve. Okay, it looks here like we're making a little table. I am not going to worry about that. Okay, let's look at this right here. Also is another table. Okay, so this here has the histogram bins in it. Those bins come from cut. So cut is a function that takes a whole range of data and it cuts it into bins and it counts up how many are in each bin. So if we look at the help for cut, and we can show this with this data. So we've got lone 50, there's the 50 data, and we can create a new variable. But it like doesn't display in the table because there's too many columns. But we can use count, and count will give us just a table of that. So we're counting up our interest rate categories, where our interest rates rather were cut into sections where the breakpoints were a sequence that started at 5 and went up to 27.5 in increments of 2.5. So maybe it's worth taking a look at the sequence function for just a second. SEQ, SEQ. So a sequence from a lower bound to an upper bound by an increment. So we can do like a sequence. So the easiest sequence is something like 1 to 10, where you're just counting integers. But this sequence gives you ways of doing this differently. So we could go from 1 to 10 by 2. Oops, close parenthesis. So it started at 1 and it went up to 10 by 2. It doesn't print 10 because 10 is not in the series starting at 1 and going by 2. You can also go by fractions. So you could go by pi. And we could start at 0, say, and go by pi. 0, 3.14, 6.28, and so on. You can see another option here is length out. Length out. So we could do this in 11 digits, right, which are the integers from 0 to 10, or you can do it from 110, say, integers or values, and then it's going to give you equally spaced values from 0 up to 10 by, it figures out what the by is, what the step amount is, in order to give you a total sequence that has 110 values. Okay, so that's what that is doing, this sequence right here. 5, 7.5, 10, and so on, and that's the ranges that you see here or in this table that we made this way. Okay, you get these cut points as the boundaries. There is a way in the cut to make in the cut function to make the lower bound be inclusive rather than the upper bound be inclusive, right? Closed interval, open interval. Okay, anyway, so we've got that. We're separate. That's just making the table though. All right, so let's make the histogram. So we've got our data set, we've got our interest rate, right? So what components do we need for a histogram? We just encode interest rate to the x-axis. Our histogram automatically is going to give us our y-axis for the frequencies or counts. We might need to specify the width of each interval of our bins. So in this case, I'm going to show you the default histogram first. Okay, so if you just put in X as the interest rate and geom histogram, you will get a little note down here that says bins equals 30. So by default, it creates 30 bins. 30 is sort of a nice default, and it adopts that. So here we're going to do breaks, and we're specifying specific breaks, okay, to match this table that we had. Okay. Another way to do that is, let me look in geom histogram. Geom histogram, bin width. So you might do something like, instead of specifying these breaks, so you can do bin width equals, and those breaks are 2.5. Okay. Now we've got a very different looking histogram, and that's because, if we go back a moment, the first histogram, we specified exactly where the end points, the edges of the bins are, the break points. It starts at 5, then 2.5, and then 2.5 more gets us to 10, and so on. When you specify the bin width, it basically chooses the minimum value to be the left border of the lowest bin, and the maximum value to be the right border of the maximum bin. We can test that theory by adding geom rug to the plot, where the rug are the individual points here. So there's actually some space on these in here, so it's not the minimum and maximum that specify the bins. So now I don't know how it's choosing the bin edges. Maybe it's being smart about this, because they are sort of centered at these whole numbers. 20 is the center of a bin, and then there's a few bins, and then 10 is the center of this bin. So it's, anyway. So it has some algorithm to do that. But if you want to control it explicitly, you can do that with the breaks. All right, the next is just the labels, and then we're putting the percentages into percentage. So we've seen all this before. The only other part here about the x-axis is we're specifying the breaks. And so the breaks are the labels that appear at the bottom. And these breaks were 5 to 25 by 5. So we've got 5, 10, 15, 20, 25. It's going in increments of 5. So I almost always specify those breakpoints to be easy to read for the context of the problem. All right, so the next one is these density plots. So this is basically the same idea. In fact, this code is almost the same, top and bottom. The difference being that instead of a histogram in the top, we're plotting a density plot instead down here. So I'm going to show you the basic one. All right, there it is. Now let's look at some of the options under geom density. In particular, there is something called, I think it has different names, but it might be called the bandwidth. In this case, it's the adjust. But there's a kernel, so geom density histograms are sort of a complicated idea. The main idea, in fact, let me add to this geom rug. Okay, so we can see where the individual points are. Okay, so there's the individual points. The way it works is that for each point, you put a little curve on top of the point, like a little hill. In this case, the hill is a Gaussian curve, a normal distribution. And so for each point, you've got one of those normal distributions. And then you're going to add them all together. And when you add them together, you get this density curve, which is the top of having added all of those points together. The adjust part here adjusts how wide each of the curves is. Okay, so let me copy in here. The alpha part doesn't matter. So adjust 1. That means that each, I think that means like the standard deviation or something of each normal distribution is 1 unit. So if we set that to equal, how about a half instead? Now you've got something that's a lot more wiggly because each curve is very narrow. In fact, let's go to the extreme. You guys ready to get extreme? There's all of our individual distributions, right? They're very, very narrow, and they're not overlapping. As we make them wider and wider, the tails of the distribution start to overlap, and then, you know, more of the distributions overlap. If you make each distribution too wide, then you sort of lose all resolution completely. So this is definitely a parameter that you want to adjust when you are making one of these plots, because the features are either hidden or it's too noisy. So there's something in the middle that's going to give you a plot. Like this one is pretty good, but there's a lot of like small wiggles. It's like a little bit too detailed. 0.5 might be about right. This one's starting to look nice and smooth. You see that there's a peak here at 10. You see that there's another peak here at like 18. And those are the main features. And it's right skewed. There's a couple observations out at 25. So that seems like the level of detail that is appropriate for this plot to me. And so mine actually has more detail than the one that they provided in the book. All right, let's see what's next. These are just histograms to discuss modality of plots: unimodal, bimodal, multimodal. You know, bimodal is actually multimodal, but here we're talking about multimodal being more than two modes. Okay, mean variance. These plots are sort of neat in that, like, what are these gray bars? These gray bars are representing standard deviations behind the data. I will show you that just real quick because the concept is sort of neat for plotting that stuff. That's this part here. In fact, I'm going to make a couple changes here because I want these boxes to be a little taller than the data. Okay. The idea here is that we've calculated the mean. Oh, I haven't because I skipped over it. Okay. Now we've calculated the mean. The mean, and we've calculated the standard deviations. Okay. And let me so there's the mean. One standard deviation is about 5 units. Okay, so SD1 is one standard deviation from the mean, and this little table that they're creating are the corners of a box. They're going from the mean minus one standard deviation, which, right, the mean was, say, 11 minus 5. So 11 minus 5 is 6, and then 11 plus 5 is 16. So we're going plus 1 and minus 1 standard deviation from the mean. And to make a box, we're going to change the y-axis to go from 0 up to 20, and that's going to give us a rectangle. And then we're going to do that for 2 standard deviations and for 3 standard deviations. All right, so we make our 3 boxes, our data for our 3 boxes, and then we're going to make this plot. So let's start with a plot that just has this histogram. Okay, there's our histogram. Now the next 3 lines make these polygons. So let's add those. So we've got 1 box in the middle, 2 boxes. The medium gray is our second box, and our light gray that goes all the way out is our 3 standard deviations from the mean, where the mean is right in the middle. Okay. You know what I would have added to this? We should at least know where the mean is. So we can do a geom V line, that's a vertical line, where the x-intercept is equal to the mean. So let's put that down here. And let me make sure that I've gotten just that part right. Okay. Yeah, there's the median, or the mean line, excuse me. Okay. So now we've got where the mean is, the center, plus or minus 1, 2, and 3 standard deviations. What I might have done instead, because the grammar of graphics has layers, is I might have put the polygons in the back. Let's do that. Let's do the polygons first. All right, so let's start with the polygons. We'll see what that looks like. There's just the squares. And then on top of that, add the histogram and then the vertical line for the mean. Now we don't have our bars or those shaded regions obscuring our histogram. We want our data to be in the front, but we want those gray bands to be reference points. So let's put them in the back where we can see them, and we'll put the mean right out in front because it's not really obscuring the data. So that would be my preference for this plot. Looks like we're doing percentages, and then we're removing some. So we put some percentages down here, and panel grid major X and major Y. There we're just changing the grid pattern. These white lines in the back. Here I've gone back to the original. See all the white grid lines? So if I come forward one plot, we've removed some of those. For the x-axis, we've removed the major and the minor grid lines, and for the y-axis, we've removed only the minor grid lines. So the major ones are the ones at the labeled points, and the minor grid lines are the ones that go between. And there's plenty of control. You can control where the breakpoints are. There's break, and then there's break minor, and you can specify values for those. All right. I'm going to sort of skip over this. It's the same as before. Here they're just making dot plots and box plots, so nothing really interesting there. Oh, are those exercises? No. All right. Here's just some more dot plots where they've manually colored one point. These are transforming data. Let's go to transforming data because I want to talk about log scale. All right, so while we're going, I'll just run each of these chunks that are here so we know what we're missing. Okay, there's a table. Transforming data. Okay, so this I think is the cool stuff. Yeah, log base 10. All right, so let's start with, in fact, did I already put in log? Okay. Let's work with one. Okay, I think this is the one. Okay, this is the one that I did in preparation for this. So I'm not going to worry too much about the log scale on just this one because let's do it on this scatter plot instead. So here's a scatter plot where we've got population on the x-axis. Oh, population before a change. I'm not sure what the change was. Hopefully it says up here. Oh, from 2010 to 2017. That's not very long. It looks like a huge difference. Oh, and then population change on the y-axis, and maybe that is a percentage. So we've got millions of people on the x-axis, and then probably a percentage on the y-axis. So some places go up and some places go down. There's lots of changes for small places with small starting populations, and it's harder for lots of people to change where they're living when the population increases. If you take the log scale, this is log 10, right? So log 10 are powers of 10. So 2 would mean a 1 followed by 2 zeros. So 2 is 100, 3 is 1,000, 10,000, 100,000, 6 is 1,000,000, 7 is 10 million. So we have log transformed the y-axis, and we've spread out the data. So now we can see more of the information in the data. There's so much in nature that follows logarithming, the log scale, or is exponentially distributed, like like lengths of things, weights of things, metabolism rates. There's all these allometric scaling. Let's see, allometric scaling. And in fact, here at the University of New Mexico, we have one of the world experts in these laws, along with Jeff West at the Santa Fe Institute. This is one of the early papers on this. James Brown is one of the experts on this. And I think Brian Inquist is one of James Brown's students. So anyway, there's all these laws or all these relationships about allometric scaling. So like how does metabolism scale with body weight and respiration and the number of heartbeats? Like the number of times your heart beats in your lifetime is sort of constant regardless of your body weight, but when you're small your heart beats really fast, and when you're big your heart beats slow. So there's all these cool things. Anyway, so doing things on a log scale often makes sense. There's a distribution called the log normal distribution, where on the original scale where things are exponential, they're not normal. But if you take the logarithm of them, now the distribution is close to normal. Like this here is maybe roughly close to normal along the x-axis on the log scale, but definitely super right skewed on the original scale. Okay, all that with background, let's start looking at some of these plots. The main thing I want to show you is two ways of doing the log scale in a ggplot. So here is a basic plot. So we've got population change on the y-axis, the population in millions on the x-axis, and we're going to plot the points. So here is that plot. The rest here is just we're going to change the labels by scaling to millions and label the axis. So that's pretty simple. So now we've got 0 to 5 millions, 8 millions, 10 millions. Haha, this is interesting. Okay, we've got these breakpoints. It goes from 0 to 2 and then 2 to 5. Right? Obviously, this is 2.5. And then this over here is not 8 but 7.5. So this this axis is driving me crazy. All right, I'm going to show you something else here. We can put in here, in fact, I will always try to bring up the help for these things, because this is how I learned how to do it, and it's how you'll be able to figure out what the options are or arguments are of a function and how to control things. Here we have breaks and minor breaks. So now is a good time to add this stuff. So it's got all this labels and stuff. Before that, we're going to do breaks at, so we're going to make a sequence. It's going to go from 0, I guess it goes up to 10 million. Okay. Now that's one way of specifying 10 million. If it's hard to count so many zeros, you can say e to the 6. Okay, 1e6 means 6 zeros. Oh, that's funny. How about 1, 0, 0, 0, 0, 0, 0? Okay, now you know that they're equal. So we're going to make a sequence that goes from 0 to a million by, how about 1e5? Okay, you can always run a piece of code like this. So every million, it's going to display, but that's a little bit too common. So let's do every 2 million. I really like breaking tens up by 2s, because if you do 2s, it's every other, and that also then allows you to do breakpoints by 1s. So let's see what that plot looks like. Oh, do we not like that? I think because we're going up to 10 million. That's why. So I'm going to increment the number of zeros on both of these. There we go. Now we're going up to 10 million, and it's every 2. 0, 2, 4, 6, 8, 10. Okay. The other thing is the minor breaks are already specified at the 1s, but let me show you what it would look like if we made more of them. Okay. So I'm going to add here. I just copied the code because we're basically typing the same thing. We're going to do minor breaks. That's this argument over here. And let's do that like by every, we're going to go every million, oh, we're still going to go up to 10 million, but we're going to go, how about 5 units in every subscale? So by every 2 times 10 to the 5, so that's every 20, 5 zeros, every 200,000. Okay. Anyway, all we're going to see here is tons of lines, right? So that's all we did. Every 200,000 there's a line. So there's 10 lines that get you up to 2 million. All right. So that's breakpoints. Okay. All right. We're coming back from the aside. We're going to do logarithm stuff. So now we've got the same plot as before, but now we're going to calculate the log base 10. There are special functions for the log. There's a log, and the default base is exponential 1. So exp1 is going to give us 2.71828.1828450. Wait, 2.71828.182818828459045, and so on. Okay. You can also do log base 10 and log base 2 are functions. My favorite log is 2 for most data, because log base 10 means that every unit is 10 times more than the previous one. But very few data sets have such a range of from the min to the max that spans, hundreds, thousands, 10,000s, like in the range. But almost every data set has a few doublings. So log 2, you get every unit is a doubling. So you go from 1, 2, 4, 8, 16, 32, and then you can have like 8 or 10 units, and each one is a doubling. It's log 2 I love. It's easy for people to interpret, and the units are close enough together to understand. But here we're doing, you can also, instead of log 10 as a function, you can specify the base to be 10. And that's what they're doing here. They're doing the log of this population, and they're taking the log base 10. And so if we do that part, we will get our basic scatter plot, and the units here are log base 10. So 2 is 10 to the second power. So you count the zeros. 100, 1,000, 10,000, 100,000, 1 million, 10 million. So 10 million is still this maximum point, right? All right. The rest is just labeling. Another way to do that in ggplot is to label them on what the log value actually is. So there is a function called scale log 10, and you choose X or Y or fill or other color to be whatever the visual attribute is. In this case, we're doing the x-axis. We're going to just change the scale. So we're plotting the original variable, population x, but we're going to change the scale of the axis. So watch the axis down here. It should look identical, except the labels are going to change to be the values themselves. So if we go back and forth, you can see the plot didn't change at all, but the labels did change. Let's add some stuff down here into this log 10. Let's take away the breaks and just focus on, because maybe these other labels will make this easier to read. Okay, there's 0 million. Wait a second, this is also 0 million. We need more, maybe we do need those breaks. So let's see if all this helps us make sense of it. That's pretty good. So the lines down here, like this 2 million is way over here, right? And then 4 million is there, and 8 million is there. You can see like most of the scale is off the charts, because most of these places, I guess, have fewer than 2 million people. Okay, So we actually sort of need more density of points down low. We can get that by putting in more points, more breakpoints. Does that help? There's 1 million is here. Okay. So the main thing here is that you can do on the units of the log for the x-axis. Okay. Like we don't even, the way I've created the sequence, we don't even get down to the 100,000, 10,000. But we could make the breakpoints explicitly that, right? Let's create a sequence that gives us what we want. So we want a sequence. Oh, how about this? 10 to the power. Okay. And we're going to do a sequence from 1 to 7. Aha. Okay, so now we've got 10, right? 10 to the 1 is 10. 10 to the 2 is 100. 10 to the 3 is 1,000. So that is the sequence of our breakpoints that we want. Okay. And I'm not going to worry about the minor breaks. It was enough to just figure out what the major break should be. And you know what? These the scale of millions is not really working for us anymore. Let's do something like, how about thousands? So 1, 2, 3 zeros. We can do thousands, so that's K. And we'll try that. So we should have point. Is this working? 0, 1,000, 10,000, 100,000, 1 million, 10 million. Yeah. So now we've got numbers that are labeled with their actual units, and the scale is on the log scale. So I'm sorry if that was too long and induced some confusion, but the main thing is that we've labeled the points with the actual value of the population and just scaled the axis so that it's on the log scale. Whereas this original plot, where if you calculate the log, then you've got to figure out, possibly by computation, what 2, 3, 4, 5 mean, because you have to take 10 to that power. Okay. All right, the last part is maybe the most fun part, because we don't get to work with maps very often. All right, and maps, making maps is a whole subject unto itself. So in the maps package, there is this data having to do, which is by county, and I'm just trying to get a look at the data. All right, we've got something called FIPS. You all know what FIPS are, right? I don't know, but it looks like it's some sort of sequence, right? So it starts in Alabama, and Alabama is the state, and the second word is the county name, and this is the number that goes with that. Why don't we learn something together? County FIPS codes. Okay. So this looks like zip codes, but I don't think that's what it is. Oh, federal, here we go, Federal Information Processing System. Okay, that sounds exciting. So, anyway, all that we have here are these labels. Let's take a look at the structure of this data set and see what else. That's all there is. There's the number and the county. Okay. So we're going to take that and turn it into a tibble from a data frame. The original structure is a data frame. We're going to make it a tibble. And we're going to pull out the region and the subregion, which are the names under polyname. So we're going to take polyname and we're going to break it into two parts, region and subregion. This is a regular expression which says that we want to start at the beginning of the line and extract a bunch of stuff and go until you get to a comma, and then extract a bunch of stuff that is bounded by the end of the line. That's a $sign. So I strongly recommend you to go and spend an hour doing regular expression stuff on a website. Regular expressions. Tester or generator is tester is probably pretty good. I think one of these is the one I use regularly. This is pretty good. But maybe it's not a good place to learn about them. So I recommend finding a place to learn about them a little bit, because they come up regularly. That's not where regular expressions comes from. But so maybe instead of tester, learn. Okay. All right, lesson 1, something like that. Okay. And it's a way of basically matching patterns. This looks like it's like a whole bunch of individual lessons. That's pretty neat. I wish I had done something like that. Excuse me. When I was first learning regular expressions. This seems like a good way of getting introduced to this. Anyway, there's all these special characters. /D, period is any character. Brackets. Anyway, you can do a lot with regular expressions. Okay, so this is matching a bunch of stuff at the beginning of the line. This is matching a bunch of stuff at the end of the line, and it's delimited by a comma. That's all that's happening. So from there, we're getting this data set dfips, and dfips now has the fips column, but we've broken up the other column into these two parts. Then we're going to take the map data county. Let's see what that is. So these are map data is a bunch of data sets. These are polygons. So these sequence of latitude and longitudes is a connect the dots that goes around the Alabama region, and this is the subregion, the county. So these down to here, these 51 points draw the boundary of that county. Okay, so we're matching things up, blah blah blah. Okay, it looks like there's some special considerations here. I'm not going to worry about that. And that's going to create this data set called map county. Okay. And then we're going to county complete. Let's see what that is. Oh, okay. This looks like data. Here it is. So for each FIP, state, and county, there is population data, starting at 2000, then 210, and then every year after that. The number of people who are different age groups, proportion Hispanic, proportion high school graduate or percentage, percentage home ownership, etc. Okay, so tons of information by county. So we're going to select some of those. We're pulling out poverty, unemployment, home ownership as the data that by county that's going to go into our map, and then we're going to join these two data sets together. We're going to join the map data and the data for the map. Does that make sense? The map county, I think, was the polygons, right? Yeah, these are the polygons. And to that, we're going to join the data that we want to plot. So now we've got this cool data set, map county, that has both the polygon information, but also like the poverty data and the unemployment rate and so on. Okay, so now we can plot stuff. And my goal is not to really go into this a lot. In fact, there are lots of other ways to plot data in R. There's a whole, there's packages to do this and so on. But here we've got ggplot. We've got our data. We've got our x variable is our longitude. Yep, that's like going around the equator, and Y is the latitude that's going up toward the poles from the equator. And then group is group. So group here is a number that uniquely identifies a state's county. So we're grouping each of our counties so that when you connect the lines, they're all kept together, and it's separate for each group. So if we do this first part, we've got a set of axes, which are the longitudes from -120 to -70 or so, and latitudes from 25 to 50. To that, we're going to add polygons, and we're going to fill it by poverty. And every county now is going to be filled with, because it's a numeric variable, it's filled along a color bar. So basically very dark blue to light blue. Poverty level here is from close to 0, right, up to 50% in some of these very less populated counties. You can, if you had, say, 100 people, and you've got a bunch of people who retire to a ranch or something, then the other half of the people who live in the county work at your ranch or something. I don't know. I don't know what it's like to be rich and have a ranch. And then scale fill Veritas. Veritas is a color bar. So if we add that, it's going to change the colors to this dark blue to yellow colors, so that it really makes these higher numbers pop out visually. We have lots of unemployment down here in the south, and maybe parts of Arizona, and people in the northeast and along the, the California coast. We have low poverty. Anyway, and then the rest are labels, and removing the labels that go around the outside of the plot, because we all know where the United States is. We don't need the latitude and longitude to help us identify it. Okay, cool. And then I think the rest is just looking at other variables. Like this one is the unemployment rate instead of poverty rate. Oh, I didn't plot it. I assigned it to this. When I ran that piece of code, I ran all of this, and I assigned the plot to this object, but I didn't print the plot. I just saved it. So if I run it down here, I'll see that plot. Those are cool colors. So this Veritas, these Veritas colors, here we have option D, and down here we have option A. Those are selecting basically the min, max, and maybe the middle point of the color bar. So unemployment rate, lots of unemployment way down here in Southern California, Arizona area. All right, that is, I think, all I want to talk about. So that we've covered a ton of plotting stuff, but certainly not comprehensively. There are tons more plots you can do, but I think with these skills and the plotting stuff that I gave you in the Advanced Data Analysis book and videos that accompany that, I think you've got now a ton of skills, that you can, or at least a ton of material that you can copy and paste and modify, right? Theft is your friend in writing code. All right, see you in the next one.